All right, welcome back to Easy Math with Nick. Today we are on video number 12, and we will be deriving the period of a physical pendulum today. This is just derivation. There's no AP exam questions or anything for today, like I've been doing for the past two videos or so nothing like that. A little different of a format, but there you go, Easy Math with Nick. That was covered. Couldn't see that for a second. Okay, starting with some givens. So we're dealing with the physical pendulum of mass m and radius r, in length L, but we don't really care about the length. We're mainly concerned about half of the length, which is the radius. When it's so this rod is attached to a pivot. We're assuming that pivot has no friction, so there's not going to be any external torques or forces going on here. That pivot's at the rod's end, so the rod is going to be rotated around that pivot. And the angle that this rod sweeps out with respect to the vertical is going to be relatively small. So around less than or around 15 degrees. So this is so we could do the small angle approximation, which I accidentally included right here. Spoiled that. But we'll get to why that is important later. Speaking about sweeping out angles, we're assuming that this rod has sinusoidal motion, which just means it's going, when we look at our equation for position as a function of time, it's going to take the form of a sine wave. So because a sine wave goes between, like, looking at a graph here, very crudely drawn, it goes between two amplitudes, right? It doesn't falter from those two amplitudes. It goes to what amplitude goes. You know what a sine wave looks like. I would have to explain that part. But I won't go into too depth in that regard, but it comes up briefly later, so that's why I mentioned that. Also, finally, the inertia of this rod, because it's a rod rotating around its end, that's a standard equation usually given to you. The inertia of the rod is 1/3 mass times radius squared. So starting off here, let's draw a little free body diagram here. Draw that crudely drawn rod first for to start us off here. So we have the force due to gravity is the only force we care about here, right? Because the other force is the applied torque, the pivot force that's keeping this rod in the air and not falling down, not a free fall. So that's our force due to gravity. And we're at some angle to the vertical. So if we want to find the perpendicular component of this force due to gravity, which we're concerned with here when we're finding the torque, we're going to use the fact that this angle is going to be the same as that other angle I drew. So we can find that perpendicular component of the gravity, which is going to be sine of that angle times the magnitude of that gravitational force. So when we look at our sum of torque, of course, it's not equal to 0. It's equal to inertia times angular acceleration, I alpha. We're not worrying about negative signs, direction, or anything here. It would cancel out anyway, but that's besides the point. Force due to gravity, which is the mass of the object, the mass of the rod, which is mg, sine theta. Isn't that nice? And because of small angle approximation, we could substitute sine theta as theta, because when theta is relatively small, which is less than 15 degrees, the sine of that angle is going to be roughly the same as the value of the angle itself, when we're dealing with radians at least, which is assumed here, even though I used degrees up there, but whatever. That's just mathematical fact, so which is very helpful here. So if we continue to substitute in what we know is the inertia 1/3 mr squared, angular acceleration can be rewritten as a second derivative of angular displacement with respect to time. Theta, isn't that nice? It is. So mass on both sides cancels. So we're going to have 1/3 r squared d2 theta over dt squared. You might be wondering, why did you take the second derivative there? Why did you rewrite it like that? Because we're going to be doing that links to the sinusoidal motion thing I mentioned before. We are going to be taking a second derivative later on, not too in the galaxy not too far away. That was horrible. That was a horrible joke. Wow, holy smokes! You could roast me in the comments for that. Wow, my train of thought just completely derailed. Okay, forget it. We're doing that because it's useful for a later step in the problem. Um, but now that later step in the problem involves linear acceleration now. So let's convert angular acceleration to linear right off the bat now so we don't have any worries later. Uh, we know that the relationship between all angular quantities and their linear variance, for example, linear displacement equals theta times radius, the angular the angular displacement times the radius of rotation. Uh, this this relationship. Oh, I'm sorry. Oops, I meant to. Okay. Well, I'm messing up here. Sorry. Omega times r, and this stays true for all linear quantities. All these linear quantities. So if we're looking at angular acceleration here, going to equal to linear acceleration divided by that radius of rotation, which is our r, capital R. So we're going to have 1/3 r squared times d2 x over dt squared, because that is our second derivative position with respect to time, which is acceleration, times 1/r. This is just for formality's sake. And then we're going to have g, which is 9.81. I'm not putting that in the derivation. Usually on the equation sheet, they don't substitute g in for you. That would be unorthodox to do. But as I was saying, times position over radius. So this doesn't change anything. The 1/r's cancel anyway. So we're just converting between angular quantities and linear quantities, just without any extra work. You could just skip that step I did right there. Just go from here to here. Honestly, and your teacher might hate you, but I would not mind. Equals g times x. All right, so now we're all in linear quantities. So let's solve now for the second derivative of acceleration. I'm sorry, the second derivative position with respect to time. So let's solve for acceleration. So for the next part of the question, we don't tweak out. 3g over r squared times x. Okay, we're at the dead end now. We need something else to help us out here. We have, we want time, right? How are we going to get time from this? Multiply both sides by dt squared. Integrate twice. No, what? That would be horrible. I don't want to do that. And that would only give you a general equation for time, maybe. That's not going to work. That, ew, disgusting. We're going to utilize the fact that this rod is oscillating in accordance with a sinusoidal motion, sinusoidal form. So that's going to look like we're going to have a sine function. So our position at any given time is going to be, A is our amplitude. That's just the maximum displacement times sine of omega t. Omega, it's not exactly angular velocity. It's called angular frequency. So that's just technical. You might see plus the phase shift, which is just an initial angular displacement. Don't sweat that. That's just we're going to ignore the phase shift here. Just say there is none. So there you go. Now taking the derivative of that. So the first derivative, you can kind of see where I'm going here. Ready? Derivative of sine function is going to yield cosine, but we have the angular frequency in there, which we need to bring out because of chain rule. So the WT. And now look at what we have. Ooh, that was really sloppy. Sorry. D2x dt squared. We do chain rule once again, but we're taking the derivative of a cosine, which gets us a negative sign. So we'd have a negative out of front. Not that it really matters. We'll see in a second. W squared times that amplitude side of WT. What does that look like, right? Looks like the original function. So we could get rid of the negative. It doesn't really matter here. I won't explain why, but angular frequency squared times position. So this is almost exactly in the format we had up here, which is great. I can't express to you how great that is. So if we now let me make sure I have my units right. Yes, this is fine. Yes, this is good. Good. Give me a second here. We have units up here of meters per second squared. And we have units of meters squared on the bottom. So that's going to get us, when we look at our acceleration, we're going to get, we're going to have meters squared. That's what I meant to write that. No, meters squared on the bottom. So we're going to get, when we look at our units, 1 over meters times seconds squared. No, something is a little bit off here, don't you think? Meters per second squared over meters squared. Yes, that gets us inverse seconds, so not exactly what we want. We're missing something here. Before I continue, I think I could have made a mistake somewhere. I know, crazy, right? I make a mistake. I'll pause very briefly and fix this out. Oh, okay, just a very little brief thing. I forgot to multiply times the radius here. It's mgr sine theta, not just mg sine theta. I just included the force and not the radius. So just imagine we're multiplying by the radius of each of these steps. So yeah, that makes sense. Okay, very minor mistake there, but now we're going to have down here. That's why you check your units at every step, right? Radius times g times x. Okay, that's more like it. So oops, I didn't mean to erase all that. Now we're going to have 3gx over r. Yes, that's right now. So if we look in front of the x, we have 3g over r, which is going to be equal to the coefficient we have in front of the x here, right? So we're going to end up with omega angular frequency squared equals 3g over r. So angular frequency equals radical 3g over r, all under that radical. But this is angular frequency, and we don't want that. We instead want the period. Because we're dealing with angular frequency here, usually period is 1 over frequency, but it's angular frequency here. So it's going to be 2 pi over w is the relationship between period and angular frequency. So our period is going to be 2 pi radical 3g over r. And that's going to give us, our period is 2 pi radical r over 3g. Quite wonderful, right? That should be our correct equation with the correct units now. If we look at our units here, we have meters. And down here, we have meters per second squared. So we're dividing by meters per second squared. So we're going to have a cancellation of meters. And we're going to have on top second squared under the radical, which gets us in the units of seconds. So our units check passes here. So there you go. That's our period of a physical pendulum. So that was quite a lot of work here. The only real mistake I made here was that forgetting to multiply times the radius when we're looking at our torque here. Our torque has to be in the units of newtons meters. This is only in units of newtons. So you needed to multiply times the radius to get in the right units, of course, right? That makes sense logically. I'm not going to go over what torque is, but that I think I did in the prior video, maybe. But everything else we did right, so just had to take a pause for a second. That pause feature really is useful for when I just have to take a second to pause and don't want to waste your time. So yeah, besides forgetting multiply times r, I think we did everything else right. So there you go. That is our period of a physical pendulum in the terms of radius and gravitational constant g. Okay. The reason why I think this equation is nice too, because if we're on another planet, we could substitute in a different number for g, and have the equation be valid. So that's why I think putting in g for 10 as 10 or 9.81 isn't advantageous, because you might have wacky questions to ask about other planets. So there you go. Whatever. That was a lot of work. We took advantage of the fact that this rod is undergoing sinusoidal motion, so it's going to its motion could be represented as a function of time. It's going to look like a sine wave, and we can use that fact as when we take the second derivative of that sine wave, we are going to get the boop boop boo. We are going when we take the second derivative, we can have an expression for which we can link up to what we found using our expression for torque through all that work we did on the right. And we have two equations which have x with a coefficient out front. The coefficients therefore must be equal because we have two equal expressions, as we saw for acceleration, second derivative of position with respect to time. And so we set those two coefficients equal to each other, solve for W, which is angular frequency, and there you go, we get our period. The reason why W is angular frequency, just very briefly, when we look on our sine graph looks like this. You might remember from math class that if we have a trig equation in the form of like a sine b of x, the period, which is going to be the distance for one complete oscillation in our case, or one complete cycle of the sine wave, is going to be that period equals 2 pi divided by b, right? If b is 1, then the period is just 2 pi, which is our normal sine wave. So that's essentially what we get for our equation here, right? Our b up here was omega, was that angular frequency. And so that just correlates to what we had in this equation here, where it's 2 pi over b, 2 pi over w to get our period. So that's where we get that equation from. If you're a very graphing type if you like visualizing, if you're a very visual type person that likes looking at graphs, that's where we get that from. So besides that, I think that's all I wanted to cover today. If you really wanted to, maybe you'll see some equations that put the 2 pi inside the radical, although I doubt that. So yes, besides that, I think that is all for today. Thank you for sticking by. I don't think I made any other mistakes. If I did, let me know in the comments. I kept this video relatively short because it's just a simple derivation. So no need to drag it out. Thank you for watching, and I'll see you soon. Thank you.